Okay, so let's go ahead and get, let's do some review. So let's go back to the beginning and try a few. So first, let's so first let's draw these. The first one, you just need to complete that for Lewis dot structure. The second one, let's draw that in line form. Right, and let's draw this in a line form. And hopefully by this time, these are pretty straightforward. Okay, on the first one, we just need our lone pairs to make that a correct Lewis structure. We could have also then put in our hydrogens. So remember, when you're looking at the full structures, you've got your hydrogens. Some basic just drawing. Here, if we were doing this one, right, we have in our ether. On this one, we've got 1, 2, 3, 4. So if we count 1, 4, so that's 6, 7. So 1, 2, 3, 4, 5, 6, 7. And then we have a methyl coming off of that one. Okay, so some basic stuff. Just make sure that you remember how to do this. Don't let something simple like this throw you off. Okay, let's do a couple of nomenclature questions. We didn't focus a whole lot on nomenclature, but we did have some nomenclature. So let's draw a few of these. Okay, so just some alkanes and one alcohol. Let's take a couple minutes. Again, that's what we're going to do today. If you have any questions, please ask so that we can cover this. But nomenclature, let's take a couple of minutes to name these. Okay, so if we look at the first one, we have 5 carbons, so that's pentane. Second, we have 5 carbons, but an alcohol on it, so this is pentanol. Right? But we also need to say where the all is, and it's on the 2 position. Right? So we're gonna either number starting here with 1 going this way, or starting here 1 going that way. So you always want the lowest possible number. here we have cyclohexane. We've got 2 methyls on there, dimethyl, and then we have 1,3-dimethyl cyclohexane. And on this one, we go with the longest chain. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So both of these are going the same direction. So to help me do this, I'm going to circle my longest chain. All right, so then that gives me a methyl and an ethyl. So then, 7 is going to be heptane. And then ethyl is going to come first, then methyl. Right? And if we look at our numbering, we could have 1, 2, 3, 4, 5, or we could have 1, 2, 3, 4, 5. So we're looking at 3, 5 either way. And so what takes precedence here? Okay, it's alphabetic, right? So therefore this gets the 3 and this gets the 5. It's not the size, it's the alphabet, right? So E comes before M, so therefore the ethyl gets the 3 and the 5 goes with the methyl. Okay. All right, questions about straightforward, or it's not simple unless you know it really well. It can be incredibly difficult if you don't know the rules. So any questions about this nomenclature? Okay. Let's try some with stereocenters. Okay, so let's take some time on these. So this is stereogenic naming. So remember on alkenes, you're going to have cis and trans or ENZ. And on alkanes, on chiral alkanes, you'll have R and S. Okay, let's go ahead and take a look. For the first one, here we see the all of these are on the same side. So 1, 2, 3, 1, 2, 3, 4, 5, 6. So it's going to be hexene. And then we need to number where it's at. So 1, 2, 3. So there'd be 3 hexene. Okay, when you're naming the enes, right, you name the 3 and the 4. So this is going to be 3. You don't have to say the 4, but that's something you have to keep in the back of your mind. And then this one is going to be cis. Okay. Something we didn't cover in depth, barely covered. It was in your book. Was the fact that this could also be known as Z. Okay, and for Z is Zane Zide, right? And what you're using is more of an RNS naming system. So if you ever see E and Z, Z is same side, R is E is opposite. Okay, so cis 3-hexene. For the bromide here, right, we're going to have 1 is going to be the bromine, and then 2, 3. This gets 2 because it's a carbon attached to a carbon and 2 hydrogens versus a carbon that's attached to 3 hydrogens. Right, so we're using atomic number, not size. And so for the atomic number, right, that's where we get the 1 and the 2. And then the one that's not shown is our hydrogen. And since the bromine is coming forward, the hydrogen's going back. So if we draw from 1 to 2 to 3, we see that's going in the clockwise direction. Right? And clockwise is R. We just have to check our lowest priority, and it is back. So this one is R. So this would be R to bromobutane. Okay. Questions about that one? All right, the next one, again, here we need to number these. So if we look at the bromine, that's going to be 1. And then we have 2 in this direction, and then 3. And again, you go out and it's still got a carbon attached to a carbon, but this carbon here is also attached to a bromine. So the bromine is going to give this weight higher. So that's going to be 2 and 3. And then in this case, if we look at our hydrogen, which is not shown, it's coming forward. Okay. So 4. And then on the other side, let's do that in purple. So here we have 1. This again is 2, 3, and our lowest priority, our hydrogen this time, is back. And our lowest priority too. So, okay. So looking at the bromine, we go from 1 to 2 to 3. This is in the clockwise R direction, but where's my lowest priority? My lowest priority is back, is forward. So therefore this is not R, this is S. Okay, so this is an S. And then for my bromine, right, we go from 1 to 2 to 3 in that direction. This is counterclockwise. Right, so that's an S. Where's my lowest priority? My lowest priority is back, so this stays S. So this is going to be 3, 4 dibromohexane, and then this one is going to be 3S, 4S. If we do the other one here, starting with 1, 2, 3, we go in this direction, right? My lowest priority is back. Right? So therefore, this is going to be R. Lowest priority is back, so it stays R. The other side, we get 1, 2, 3. My lowest priority hydrogen is back. Okay, so when we do this one, that's going in the counterclockwise direction. So that's S. The lowest priority is back. So this one is going to be 3, 4 dibromohexane. And then this could be 3R4S, but this is often just said R and S. And the reason that you'll see the R and S sometimes is what's different between this one, right? What's different between this one and that one? Well, if we can compare those two, if we compare this one to this one, are they enantiomers or diastereomers? Okay, are they mirror images? Or are they non-mirror images? Well, they're non-mirror image, non-superimposable, right? So that makes these diastereomers. Okay. But if we look specifically at this molecule here, what do I have right through the middle? Well, I've got a mirror plane. Since I can bisect that molecule with a mirror plane, but still have chiral centers, I still have 2 chiral centers, then that means that this is a meso compound. And the reason sometimes you'll see the 3 and 4 left off is it's a meso compound, and so therefore it's got a mirror plane in the middle, and you don't know which one is 3 and which one is 4. It's symmetric, and so therefore leaving off the RNS actually kind of clarifies the fact that this is a meso compound. So, all right, so let's look at some stereochemistry. Let's do some comparisons. I'll draw them up, and then you tell me whether they're diastereomers or enantiomers. So we're going to have pairs. Okay, so tell me whether these are enantiomers, diastereomers, meso compound. Okay, so let's take a look. So enantiomers are non-superimposable non-mirror images. Diastereomers are, oh, sorry, that is incorrect. They're non-superposable mirror images. Diastereomers are non-superposable non-mirror images, apologize. And then mesocompounds its best definition is an achiral molecule with chiral centers. Okay. So if we look at the first one, does that look like a mirror image? So it's drawn in a way that we can show, right, there's a mirror there. We don't have to rotate it. We don't have to change anything. And you can see that, you know, this OH does not reflect directly into that OH. This OH is down, this one's up, this methyl is down, that one's up. So, and we can't rotate it around, so it won't superimpose on the other one. Wait, can we?
Yeah, I think it's super.
Yeah, it is superimposable, right? So this is actually the same molecule. Sorry, I didn't mean to do that. I'll draw you all another example. So this is the same molecule, right? So I could flip this one. So if you think about rotating it around this axis here, then it'll flop on top of the other one. Okay. One way to determine this, and we'll do it here so you can kind of see what's, if you couldn't visualize it, this is always a good check. It takes some time, but again, it's the final exam, and this may be the last time in your life you're doing this, so why not do the check? So here, if you get to 1, right, and then this is going to be my 2, and this is going to be my 3, right? So this is going in the R direction, right? And my lowest priority is back, so I'm going to stay R. Here we get at the bottom one, we have 1, right, 2, and 3. So if we go in this direction, right, that's giving me a S. But where is my lowest priority? Well, it's coming forward, so it's not S. So this is RR, right? If I go over here and I do the same thing on this side, so I get 1, 2, 3, then this is going in this direction. That's going to give me a S, right, counterclockwise, but my lowest priority is forward, so it's not S, it is R. Remember, if you're looking at it and the lowest priority is supposed to be away from you. So if it's not, then you're just on the wrong side of the perspective. So you can just flip it. So then down here for the methyl, we get, again, 1, well, 1's going up, 2's going in, 3's going out to the methyl. So 1, 2, 3 in this direction. Now we have R, right? And so by naming this, right, you can see that this is an R, R, and this is an R, R, so they're the same thing. So one of the things you can do to check your enantiomers, diastereomers, and mesocompounds is naming them. And enantiomers are always going to be opposite. So an RR should be SS. Diastereomers will change 1. So a diastereomer would go from RR to RS, or RR to SR. You would be changing one of the 2 stereocenters in diastereomer. Okay. The next one, if we look at it, it looks like it is going to be enantiomers. So let's check. So 1, 2, 3, right? So we're going in this direction. That's going to be S. Where's my lowest priority? Lowest priority is back, so it is an S. Here, if we go 1, 2, 3, that's going in the S direction, but my lowest priority is going forward, so it's not S, it is R, and so that is enantiomers. Can you have diastereomers with only 1 chiral center? No, you can't, and you can't have meso compounds. When you only have one chiral center, your only two choices are the same or enantiomers. Okay. And then the last one we can see here, this has a mirror plane right down the middle, right? So these are the same molecule, but they're the same molecule because they are meso, right? They're meso because they can both have chiral centers, right? And they're the same molecule, not because I happen to do what I did up here, which is draw the same enantiomer, but here they're the same thing because it is an achiral molecule, right? So it has chiral centers with a chiral molecule. So what you're looking for meso is a plane of symmetry. Sometimes it can be hard to see, but you can see a plane of symmetry. The other thing to check, right, for these is to go ahead and name it. So 1, 2, 3, right? We're going in this direction. Lowest priority is back, so that is R. If we look on this side, we'll get 1, 2, 3, right? Going around this direction. Now my lowest priority is still back, right? So I get S. So RS. You won't have a meso compound with the same substitutions around a chiral center for an RR or an SS. Meso compounds are always RS. And so if you think it's a meso compound and you name it correctly, that's the caveat of this checking, name it correctly, it needs to be RS. If it turns out to be RR, then maybe you're looking at it incorrectly and need to think about it, okay? All right. Okay, let's move on to some acid-base reactions. So let's look at ranking. So just give me the strongest base, strongest acids. Okay, so let's start with just these sets. Give me 1, 2, 3. 1 being the strongest acid, 3 being the weakest acid. So rank these. Okay, so let's go ahead and take a look. So if we look at the first one, these are all carboxylic acids, right? So the acidic proton is all the same. So we're not checking the functional groups here. What we're looking at is other factors. And what we see is we have inductive effects, right? So we have an electron withdrawing group, right? That's going to pull that electron density. So if we think about these, we determine the strongest acid by looking at the conjugate base. So all of these are going to have the same proton being pulled, which is that carboxylate proton, right? And so therefore the impact here is going to be the pull of electron density towards that fluorine. So the pull of this electron density towards that chlorine, and that pull of electron density towards the chlorine here, right? So this is going to be an inductive effect. And what do we remember about inductive effects? Inductive effects are going to be greater based on the electronegativity. So we need to understand our electronegativity in the periodic table, right? And then second, we need to look at distance. So unlike resonance that actually moves electrons directly, inductive effects pull electron density through the signal bonds. So therefore distance has a big impact. So if we look at the first, we have the fluorine and the chlorine, they're both in the same position, but then the last one, the chlorine is out of, is further away. So if we think about electronegativity, the fluorine is much more electronegative than the chlorine, not much more, but more. Fluorine is the most electronegative atom. And so therefore, this is going to have the ability to pull more electron density away from it. When we look at distance, we see that these are both in the same position, and then this is further away. Since this is further away, this is going to have a weaker stabilizing force than this, so less inductive effect than this, and this will have a less inductive effect than this because of electronegativity. So if we rank these, then we're going to end up with this being the strongest acid, the second, and then the third. On the second set, what we're looking at here is what is our proton, and we're really looking in functional groups. So we're looking at alcohols, right? Our functional groups are all different, our thiols and our amines. And again, sometimes it's easier to think about these by drawing their conjugate bases and thinking about the stability of their conjugate base. Right? And if we think about the oxygen, the sulfur, and the nitrogen, which three of these is going to be the most stable? Okay. Well, it turns out the sulfur is the most stable, right? And it's the most stable because we have its electronegativity is in the same period as oxygen, but it's further down, so it actually has more electrons. So with more electrons, a bigger orbital, it's going to be more stable. It has a better way of polarizing that negative. And then if we look at our nitrogen versus our oxygen, they're in the same row, but in different columns. The oxygen is going to be more stable than the nitrogen. And that has to do with the electronegativity and the stability with the negative charge of those species, right? So if we look at that most stable, that means we're going to have 1, 2, and 3. We could have also understood this by understanding the relative pKa's, right? And again, the pKa here is in the 16, pKa here is around 9, and the pKa here is around 35. Okay. Questions about these? Okay. Let's try mechanism. An acid-base type mechanism. Pretty straightforward, shouldn't take too long. Okay. So once you get that one drawn, right, it's going to be the movement here. That's the resonance. I didn't draw the chlorine, probably should have. Chlorine's out there. And let's draw a conjugate base. So draw the conjugate base to both of these. Okay, so if we look at these, what we're really asking, if the question is draw the conjugate acid, conjugate base, is looking for the most acidic proton, right? That's going to be the one we extract. So if we look here, we've got the carboxylic acid, we've got this, got that, and we have lots of alkanes. So if we look, the carboxylic acid here, because of conjugation, it's going to be first, then the hydrogen attached to the oxygen, then the alkene, and then the alkane. And whichever one you want to pick, because they're all going to be about the same. So therefore, the conjugate base, if we're going to just pull one proton, it's going to be this. Okay. If we look at the next one, it's a little bit more difficult. And again, we've got several. So we got this one, we have the alkene, and it turns out this proton and this proton would be next. Okay, and this has to do with hybridization. Sp is more acidic than sp2, which is more acidic than sp3. And although this is an ether, the oxygen just has an inductive effect. It's not stabilizing. So don't think about this oxygen, this ether. The ether acidity is going to be the same as an sp3 carbon, right? So here we're dealing with 25, 40-ish range, and then above 50. Okay, so therefore, if we draw the conjugate base is going to be the deprotonation of the, it's going to be deprotonating the alkyne. Okay, all right. Trying to cover some of the stuff you probably haven't seen in a while, just to refresh your memory. So with alkanes, it's hybridization, right? So we have the things we need to look at, or if it's the same atom, we look at hybridization. If it is, we look at resonance, we look at inductive effects to figure out acid-base reactions. And proton transfers are some of the most common and fastest processes. Okay, let's move into substitution elimination. Okay, on this one, I'm going to give you the products, the reactants and the products, and you tell me what the mechanism was. Okay, looking at these 4 reactions, tell me which mechanism is occurring. Right, your choices are SN1, SN2, E1, or E2. Okay, let's take a look. On the first one, right, we've got the tosylate, right? The TS stands for tosylate. That's this group. Oops, this group. And we see inversion. Well, first, it is a substitution, right? So first thing to say is we're substituting, not eliminating. And we see inversion, and an inversion tells us that this is SN2, right? So the stereochemistry is pointing to the direction on this one. The next one, we have an elimination. Right, so we've got an elimination. Our reaction here, whether it's E1 or E2, our product could look the same. So therefore, the product is not going to specifically tell us whether it's E1 or E2. We have to look at what's going on the reaction. In this case, we have a really good base, good bulky base, right? That suggests that we're probably going to go through an E2 because we have a good base where E1 doesn't need a good base. It just needs a base. And then RT, that's room temperature, right? Well, what that suggests is we're not adding a lot of heat. So low heat would suggest that we're doing an E2 versus an E1. If we were doing an E1, we'd want to really add a lot of energy to the reaction because we've got to go through a carbocation. So this would suggest that this is an E2 mechanism. Again, the product isn't telegraphing that. In the next one, again, we have an elimination. That's the first thing to do. I see students choosing SN2 when there's an elimination. So make sure you look at that. This one, again, the products could be the same. I'm showing trans, so that's going to be the least stable. There's no anti-paraplanar issues here. But if we look at our conditions, we're taking an alcohol, we're reacting with sulfuric acid. This is a dehydration, right? And is there a good base here? No, the only base is a little bit of water that's in sulfuric acid. And so there's no good base. I'm only adding an acid, dehydration. This is in E1, okay? And part of that is knowing that there is no good base here. So we're not gonna be driving this reaction forward like we would in an E2 reaction with a good base. Okay, and the last one, here we see substitution, but we also see a rearrangement. And like with the first one, this rearrangement telegraphs what's happening here. This is an SN1, right? If we look at our reagents, we have not a really good base. It's just a base. It's just a potential nucleophile. It's not a good nucleophile. And so we see this reaction. So, and the rearrangement tells us it's SN1, okay? Questions about those? All right, let's select a few reagents. Sorry, redraw that. Okay, so same starting material. I guess I should turn that around. It's 3 different products. So choose the best reagents. Okay, let's take a look. So in the first one, we've got the bromide here. We know we're going to be doing SN2, right? Because we have inversion, so we want to drive this at SN2, but the OH here is a bad leaving group, right? So we've got to activate that. So if we activate that, we can do that with an acid, right? Or we can do that with the tosylate. In this case, since we want SN2, what would the acid promote? The acid would promote an SN1 type reaction because the conditions would be more SN1. So therefore, what we want to do here is first convert this to the tosylate. All right, so the tosyl chloride and pyridine, and then second, using SN2 reaction process, so sodium bromide and acetone, a aprotic solvent, right? We can get the SN2 favored. In this next one, we see an elimination, and we see an elimination here to the more substituted. So the more substituted process, we've got the water here. We really just need a dehydration, right? And an E1 is always going to favor the most stable, right? So E1 is going to favor the most stable. There's no stereo control, no problems there. If we look at our arrangement, our hydrogen here, right, is going up. So we couldn't form, E2 is not possible because it wouldn't give this product because my hydrogen is on the same side as my OH. If we look at our bottom one, our next one, this is also an elimination, right? But here we're eliminating the top hydrogen. And in this case, it's the only one that is anti-paraplanar, right? So E2 has to be anti-paraplanar. So therefore I want this to go E2. So I'm going to use a good base to drive it. So T-butoxide is a good base. And again, I probably want to put this in something like DMSO or DMF, an aprotic solvent. I do want to be careful. I want to drive this to an E2. Okay. All right. There were some mistakes on the diene reactions on the quiz. So let's try a couple of those. So moving into alkenes here, but the first thing let's look at is, reactions of, one equivalent of HBr. So where some students had problems on the quiz is the first reaction here is protonation so we get a proton addition, but that proton, this is symmetric, so it's got two possibilities. So that first addition could be to the terminus, right? So either here or here, both would be the same, or it could be the internal, right? So when we think about a conjugated diene system, we have either internal or external addition. So if we think about it that way, right? So this gives us this carbocation. And what's specific about this carbocation? Well, this is allylic, right? And this could be delocalized to this, right? This one is isolated, right? That carbocation is isolated. So if we think about thermodynamics and the process here, the first one is going to be favored because it's more stable, and the Markovnikov rule is to add the hydrogen to get the most stable carbocation. So Markovnikov addition here, right? The first step of Markovnikov is formation of the most stable carbocation. So that means this is not going to be a possible carbocation out of this, right? It's a possible one, but it's not a probable one. So probably you're not going to get this because it's a much higher energy state. Okay. That means that then if we look at those two possibilities for a diene, right? So let's redraw these carbocations. So we've got this plus, and again, the second one comes from resonance. So now our bromine can come in and attack those two sites, right? This one would go to this carbocation, this one would go to that carbocation, and that gives me my two possible products. This one being known as the 1,2 addition, this one being known as 1,4 addition. Questions about these? Again, remember the Markovnikov is forming. That's a question that was had problems in exam 3. Markovnikov addition is driven by the stability of the carbocation. Okay. So we're getting close to time. So I think I've covered most of the stuff we haven't seen in quite a while. So now let's look at some alkene and alkane reactions to kind of finish out our time. So I'll draw, let's predict our products here. All right, so let's take a look on the first one. Right, we've got HBr here, but we've got the peroxide. So the peroxide means that this is not going to be electrophilic. This is going to be radical. Right? And as a radical, this is not going to be Markovnikov's. It's going to be anti-Markovnikov's, right? Because we're reversing the addition, right? And the stability. So we're extracting a proton, or forming the more stable radical, which extracts the proton. So here we end up adding the bromine to this position to get the tertiary radical. Okay, let's see. I don't think I explained that well. So let's look at the half-barbed arrows. So you have initiation and then propagation. Need a half-barbed arrow. So once for the propagation, this is the step that determines our process, our regioselectivity, right? So then that ends up giving you the tertiary radical, which then abstracts a proton to give us the bromine radical that continues on in our product. The next one, this is going to be hydration. So we add acid and water. We get a Markovnikov style addition of the alcohol because the first step is protonation and we want to form the most stable carbocation. Okay. Take the time when you're going through the test. You've got 2 hours. Take the time to go ahead and show that first step of the mechanism so you can see what's going on. It's fine to have another piece of paper to work on. Just make sure it's not your notes. And then here, we get the transalkene. Okay, so sodium in ammonia, not sodium amide. They're different, and it's an easy distractor to put on a multiple choice test. Okay. So now let's look at some, choose the reagent. Okay, let's go ahead and take a look. Again, you'll have more time than this on the exam. So if we look at this one, this is an anti-addition, anti-Markovnikov addition. All right, so analyzing this, we see that it is a syn addition. So turns out we can get the anti-Markovnikov and the syn addition by using hydroboration oxidation. Okay. So those are our reagents. So we're going to do hydroboration oxidation. And the second one, we end up getting a ketone. Remember that the ketone comes from the enol ketol transformation, right? So therefore, what we want to do is put an alcohol on that second position. So we want to add an alcohol here because what we're going to end up getting is the enol, which then tautomerizes to the ketone. So we want to put it either Markovnikov or anti-Markovnikov. In this case, right, we want to put it Markovnikov. So therefore, we can use water, acid, and for alkynes, especially terminal alkynes, yeah, for internal, water and acid usually will work, but for terminal, we need the mercury. It won't work without the mercury salt. Okay, so our reagents here to give that. This last one, we got two different possibilities. Well, never mind. We got two different possibilities. I'll just redraw it. Right, we could use the peroxy acid. So this, right? You also see MCPBA, and the PBA stands for peroxy benzoic acid. So if you don't see the three oxygens, look for MCPBA. But we could have also done this by doing the halohydrin. Oh, wait, it's going to give me the wrong isomer. Right, and then followed that by, you know, sodium hydride. Just a quantitative base. All right. Okay. Okay. Any last questions or things you'd like me to touch on before the final exam? Feel free just to shout it out. syn addition. So the question is, what is syn addition? So when we look at a double bond, and we have our groups added, if I add both of those groups to the same face, we use face here because of the plane, right? So the same plane, this is going to be syn addition. If we look at an alkene and we're adding across that alkene, and in this case, we add to two different faces, right? And this is going to be anti-addition. Right, so things that are syn addition would be, hydrogen and palladium on carbon, the osmium tetraoxide. By definition, the epoxide formation is syn. For anti, right, then we have things like Br2, right? Now things like, let's say HBr, since it goes through a carbocation, doesn't have a specific syn or an anti, right? Because it could do both. So when we think about things that go through carbocations, it's non-selective. So HBr would be non-selective. Water and acid would be non-selective, so forth, so on. The other anti would be the oxymercuration. Demercuration is usually considered to be an anti. So, epoxide ring opening, it would also then, the second step would be considered anti, but okay. Well, okay, so achiral. Okay, so when we're looking at molecules, an achiral center is going to be a carbon with 4 different groups. Okay, so that's a chiral center. Okay, but a molecule can either be chiral or achiral. For a chiral molecule, right, that means that it's going to be non-superimposable with its. So in this case, right, we have that and this, right? But if we look at achiral, if I had put that oxygen in the middle, right, I now don't have a chiral center, right? There's no chiral center. And I can also bisect that molecule with a plane, right? So I can take and I can bisect the molecule with a plane. So in a chiral molecule, I can't bisect the molecule. There's no way to draw a plane of symmetry through the chiral molecule. In an achiral molecule, I can. So I can bisect this oxygen and hydrogen and the hydrogen going back with a plane of symmetry, and that makes this half and that half the same. Okay, so achiral is that definition, that I can bisect it. At least the two halves, in some cases even more than that, are the same. If we think about just an alkane, what the plane of symmetry is actually the paper, right? It's because you have a hydrogen going back, you got a hydrogen going forward, hydrogen going forward, hydrogen going back. You can bisect these, and these hydrogens would reflect into each other. Okay, other questions?